All right, we begin our next chapter, chapter 10, with the first section of sequences. A sequence is, the way I view it, is simply a list of numbers. But what's important here is that there is a specific order to these numbers. So if I swap, for instance, maybe the first and the second number in the list, then I obtain a new sequence. So the order is really not only the values, but what order they appear in. That's what defines the sequence, and that's what distinguishes two distinct sequences. So some examples here of the actual sequence written with all the terms just listed out. Then we also have a more compact way of writing it, such as a general term. So here, this is really a way of saying we have a function of n. Usually when we have a variable that is a discrete variable, in other words, it only takes on set values, like whole number values. It doesn't take on every value in between. These functions are called discrete functions, and typically a subscript notation is adopted for the variable of that function. But really, this is no different than just writing f of x. But here, this is usually meant to denote a continuous variable versus a discrete variable. So that's one thing you can think about. Okay. So if this is just a function of a whole number n, then to obtain the actual numbers in the sequence, all we have to do is plug in different values of n. N equals 1 corresponds to the first number in the list. But sometimes you may find yourself that so actually, this is a great example. This first one here, n equals 1 does not correspond to the first number in the list. It actually corresponds to the second number. And that's because the value n equals 0 actually does make sense here. There are some sequences where plugging in n equals 0 doesn't actually make sense because of some domain issues, such as is the case with the second sequence. Here we have a 1 over n appearing in the general term for the sequence, and of course that, we can't divide by 0, so the actual domain for this discrete function, this sequence, is for n greater than or equal to 1. Now typically, you'll find most sequences beginning with 1 or 0. There's no reason why we couldn't start with something else, but really, it's a list of numbers that goes on forever. And if we want to think of we can call them the first, second, and third numbers in the list in the sequence, or we can start with counting by 0. The actual number we begin with is not that important. Okay, another thing here that's interesting is not all sequences are generated by a formula. So for instance, this sequence here, it is a sequence. It's a list of numbers, goes on forever, has no end. And to find the next number in the sequence, we just need to find the next digit in the decimal expansion of pi. There's no formula that exists for the digits of pi, so not every sequence has to have a formula, but there is some way to, there is some rule, there is some way of thinking about it. So let's take a look at this first example, an example of a recursive sequence. So this word recursive essentially means that if we want to know a term in the sequence, we have to figure that out by relating it to a term that appeared previously in the sequence. So that's exactly what this is saying. If you want to know the n plus 1th term of the sequence, then you need to know what the previous term is, the nth term. So what we can do for this recursive sequence is if we are given some starting point, in this case a1 equals 1, we can go ahead and write out what the different terms are. So a1 is 1, a2, n plus 1, right? This is 1/2 the value of the previous term plus 2 over that previous term. So then you can figure this out. This is going to be, what do we have here? This is 1/2 times 1 plus 2 over 1. So 3. So 3/2. And then we can figure out A3 by doing the same thing. It's a half times the quantity, the previous term, plus 2 divided by the previous term. So I'll just divide by 3/2 and write this as 2/3. So this is a half times the quantity, 3/2 plus 4/3. Common denominator here. There's a lot going on. You can see how this is sort of a pain to compute, but the important thing here is this is the very idea and nature of what it means to be a recursive sequence. If you want to know terms farther down the list, it depends on information of terms earlier in that list of numbers. In this case, the next term in the sequence depends on the value of the current term or the previous term. All right, we can do some of this arithmetic off screen. Getting a common denominator, we see that that is 17/12. And now the fourth term of this sequence, rinse and repeat. 1/2 times the quantity, 17/12 plus 2 times, well, the reciprocal of that. So 12/17. And we have 577 all over 408. There we go. So another example of a recursive sequence, one that is fairly well known, I would say very well known, and probably all of you have heard of it, or at least at one point in your lives, and that is the Fibonacci sequence. And I'm probably going to spell that wrong. Let's say that's it. So the Fibonacci sequence, in this case, listing out the terms, we have 1, 1, 2, 3, 5, 8, 13, so on and so forth. So what we're actually doing here is, in order to get the next term in the sequence, so for instance, how did we get the number 8 here? Well, we took the previous two terms, added them together to get 8. So 5 plus 8 equals 13. 1 plus 1 equals 2, so on and so forth. So in order to actually fill out this entire sequence, we need the previous two terms. So for the Fibonacci sequence, we could say the nth term is going to be the previous two terms, so the n minus 1th term plus the n minus 2nd term. And then we have to also provide where the 0th term and the first term are both value 1. Then this information will uniquely generate the Fibonacci sequence. We could use the same rule of assignment, but give two different initial values, and that would create a Fibonacci-like sequence. It's in a very similar group, but it is a different sequence.